So the handout is for everyone. Just look at it on the front and that's it. So if there is not, it is coming. What? Yes, you are allowed to look at the front. So I just need one for me. They may not be enough for everyone, and we can run more copies later on. So there is for this section. Okay, the adult audience can take a look at the first several pages, including the problems on page 5 and 6, but nothing beyond that. So page 7 and on is off limits for everyone here. You guess what is on these pages, so leave them out. So I'm going to be working mainly with the kids in front. So I'm going to be ignoring all the adults. But before we start, let me tell you a few things about what's going to happen. So we will try to emulate a real session here of the Berkeley Math Circle. How many kids here have come to the Berkeley Math Circle? Raise your hand. So we have 6, 7. All of them are Berkeley Math Circle kids. And they volunteered, put them down, their time to come here. The problems that I have taken and going to be using today are from the book Mathematical Circles. This book is very much related to our conference. One of the 3 authors is Dmitry Fomin. Dmitry, are you here? Yes, he's here. I believe he's one of the authors. You're the same Dmitry? Most definitely. And the book is translated by no one else but Mark Saul from Russian. The problems are either straight from the book or paraphrased by me. And actually, I have given these problems at my final exam for my topics class this year at Mills to students who had never participated before in math circles. They had never been taught problem solving, neither proofs. So for them, this was a really uphill final exam. We'll see what will happen here with our kids while doing the same thing. So the problems you see there on page 5 and 6 and 7, whatever these are, they are Mills' final exam for untrained students. If you, for the adults, want to read more about the Berkeley Math Circle, the first page tells you just a little bit. This is a printout from the website. And the other, page 2, 3, and 4, are the program, academic program for this year. For example, this coming Sunday, we'll have Helmer, who will be giving a talk on, hold on, I forgot what we negotiated, observing the sun and the moon in different parts of the world. He says there's going to be a lot of math in it, and we trust him. Okay, if there is time in the end, I'm going to ask questions. If not, I'm going to be here afterwards, and you can come and talk to me. So problem 1 is the following. We have a 1 by 20 board. Okay. And we have 2 pawns, which are placed in the first 2 leftmost cells. Well, this is too many boards. I'll just need 1. So we have something like this. Okay. So what are the rules of the game? There are two players that are playing. Alice, who is captured in Wonderland by the evil queen. And they are doing the following. At any moment, they can pick any one of the two pawns and shift it one square to the right. The pawns cannot jump over each other. They cannot be in the same square. Okay? And Alice wants to escape the queen, which means she has to win this game. Does Alice have a strategy to win? And she also has to choose if she wants to be the first or the second player. Okay? So let us play in groups here, and then we will talk about it. I give you just a few seconds to play. So place your first two pawns and start moving one cell to the right by exchanging. Yes?
What are you trying to do?
Oh, I'm sorry. The obvious thing. The player who cannot move loses. So you should not be the last one stuck there, not being able to move. Okay? So place the pawns in the beginning and start playing. And remember who started first. Okay? You want to play with me? Okay. Come on over here. Okay. We will just demonstrate this. You want to play first or second?
First.
Okay, go ahead. No, where were you? You were here. It's okay. What happened? Who won?
You did the second player.
I was the second player and I won, yes? Don't tell how to do the problem, Aviv. Just tell me who won.
The second player always wins.
Oh. Okay, well, let's try here. Who won?
Second player.
Aaron says second player. Who won? Oh, they didn't yet finish. They have been thinking very hard. Okay, Aviv. So, give me a strategy for the second player to win.
Well, for one thing,
Don't overdo it.
the first player has to move this, and then you just follow it with the second piece.
Uh-huh.
So
Okay. So do I understand this correctly? Aviv says the first player has to start moving, the first pawn, the rightmost pawn, right? And what does the second player do?
He just takes the other pawn and follows it.
Follows it. So he squishes him from the back, right? And then the first player, what can he do? Nothing except the first pawn. And then the second player is very persistent. He'll squish him back like this. And they'll keep on going like that. Is everyone understanding what's happening? First player moves the first pawn, because cannot do anything else. The second player follows. And they move on like this until at the end, there the first player moves and the second player, wins. Right? First player cannot move. All right. What was that comment that you said about the word always?
Well, the second player always wins. Well, it really doesn't matter how you move, because no matter what, it takes the same number of moves to reach the end position from the start position.
Right. So, for example, if you're the second player and you don't know what's happening on the board, Okay, would you win?
Yeah. If you're the second player,
Right.
you just
So how many moves are total in the game?
36. You just this one has to move 18 and this one has to move 18.
Uh-huh. So he says there are 36 moves altogether. Is that right? Okay, so how many moves does the first player need to go? Well, there are 20 cells overall, right? So the first one needs to go only 18. And after the first one goes 18, the second one has to move also 18. Now, these moves are not made in this order, but no matter what, right, we'll have 36 moves, right? So if we have 36 moves, who finishes the last move of the game? The second player, right? So what kind of a game is this game called? Is this really a game or a joke? It is a joke, isn't it? They're joking on the first player, because the second player can win with closed eyes. In fact, they are finitely many strategies for the second player to win, but all boil down to move whatever you like at any moment. Right? That's nice. So Alice will definitely win. Okay, so let's change the rules now. Okay. We can now move each pawn to the right any number of squares we wish. Okay, so I can move the second one any number of squares I wish to, but I cannot jump. All right, play and see. Same ending result. If you can't move, you're fried. Yeah. You want to play with me?
When you said any pawn, any number of spaces, does that mean you can just move both pieces to
No, not together, just one at a time. Let everyone play. Marina, do you guys want to switch so the two girls can play together and I'm going to play with you? I want to play against you. And there is a book. Okay, give the two pawns to them and I'll play with you up there. Okay. You want to play first or second?
Second.
Second. All right. You want come around. Come around. No, come this way. All right, let's cut the chase. You should be more bold. Yeah. Okay, so what do you think?
Same thing.
Same thing. What is the same thing?
It depends on what the second player does. If the first player moves over here,
What can the second
player can do over, like, for example, over here. And then if the first player over here, then the second player will lose. If the first player.
Right. But if you want to win, which player would you like to be? Second player. Okay. So what's happening here?
So then I move here. It seems like it's the trailing game again.
So who do you think is going to win?
Well,
Well, what's the strategy?
well, same as
Just
before.
following that
See?
Squishes again from the back.
Yeah.
Okay. I won't even ask you guys. Okay. Morika has the answer, and she actually even advanced further than just giving me the straight answer. So, who would you like to be? She wants to be the second player. Would you like to play against me, or would you like to just say what will happen? She does not know. So let me choose for her. She will demonstrate for you. Come on over here. Okay, so I'm the first player. I'm going to go like this, very bold. She's following. Oh, how about that? Okay, she looks like she's squishing me from the back again. Okay. Whoops. And unfortunately, thank you, I lose. But she said something else to me. If the second player messes up, what would happen? First player has a chance to win. Okay, so everyone saw what the strategy of the second player is. It's exactly like in the previous game. Squish the first player from behind, don't give him any chance. Eventually, second player wins. How many strategies does the second player have to win this game? Tom? Yes, Aaron? As I told you, parents are the ones most interested in answering questions at the circle. Yes, Aaron?
Just one.
Just one. Why is it just one?
Because any move that isn't in the strategy can lose.
Can lose. That's right. So basically, anytime the second player decides not to squash the first player, but just does something else, the first player can take over and play the second player's strategy and do like this, yes? And then the game is flipped around. First player is chasing the second player from the back and will win. So is this a joke, this game? It's a joke? You think so?
Yeah.
You can play it with closed eyes? Not knowing what the other player plays?
No. You
Move it until it stops.
But I see. He moves it until it stops on his... No, but you're not supposed to know what the other player does. You just give instructions. So Victoria says, no, this game is not a joke. You actually have to pay attention to what's going on. All right? Now let's move on to a new set of affairs. We will be able to jump. We will be able to move again only one square to the right, like the first game. But if the two pawns are next to each other, the player has the option of jumping 2 squares forward. Okay? So jumps are allowed. Again, no two pawns, the 2 pawns cannot be in the same square. Okay? Yes, Victoria?
Can you choose which pawn you use?
Yes, at any moment you can take whichever pawn you like. All right? So go ahead and try. And let me give you this, if you'd like. There you go. You want to play? Okay. You want to be first or second?
Second.
Come here. Okay. Okay. Did you guys play it? So who won?
Well,
The
it
second player won, but the
it
first
was
player
a
started
game.
like
It
that.
was a
And
game
just
of
jump over each other.
leapfrog.
Hold on. Which player won? The first or the second?
Second.
The second. And how
It
did you
was
play?
like leapfrog.
But you don't have to do this, right?
No, you
So
don't
at
have-
some point, so try another game. That
Okay.
is, if one of the players doesn't jump and does
I
something
know,
else.
but we verified that the squooshing strategy turns into leapfrog and backfires.
The squishing strategy. Okay, that's complex English here.
Because the squooshing strategy is like this, but then it goes like. Actually, it depends on how you would move it. I mean, if The second, I mean, if the
Can you prevent this pushing strategy?
if the first player went like this and the second player went like this, then the first player would win, even though the second player would otherwise win. It sort of depends on how many squares they are from the end.
Okay.
I mean, if say it was like this.
Would it change if it had 21
so
squares?
let's say the first player did
Yes, it was. So what did you guys figure out here?
Figure the second player wins.
How?
Well, let's imagine a game played. Both players only use jumps.
These are like two possible first movements.
Okay?
But they can mix.
No, but suppose they only use jumps.
Okay, I suppose they only use jumps.
Yeah,
Okay.
Then
actually-
the second player wins.
Okay.
But let's suppose. So the second player, if the first player has always used jumps, the second player always uses jumps. But then let's say the first player decides to break. So he breaks.
Okay.
But no matter where, it has to be the two pawns in this position, right?
Breakout.
Which is like when the breakup happens, it means that the second player, allowing no jumps, would get it to here evenly. So as soon as he plays this, the second player's goal is to allow no more jumps, i.e. keep this away from this one.
Okay, but in the very beginning, what happens? What can the first player do?
Okay? Here, I'll play against you.
Okay.
I'll play against you.
Okay, all right. Come on here. Okay. Yes, now stay there. Okay, so Aviv claims that the second player can always win, but the explanation was a little bit harder than the previous games. Okay, so if I go like this, I'm moving the first pawn.
Now, the second player's strategy is just to not allow any more jumps, because we've seen that if there aren't any more jumps, then he wins all the time.
Uh-huh.
So, in order to not allow any more jumps, he wants to keep this one as far away from this one as possible.
So he
just
moves
moves.
forward. Now, even if I try to get to a jumping position, he won't let me. Okay, and even if I keep pushing that pawn forward, we'll just get closer to the end. Okay, so eventually, let's say we're like this. Okay.
And it will be my advantage because of
It
the
will
previous,
be,
because
exactly.
of the first game.
Okay, well, that's as far as this goes. Now, suppose first player doesn't move the first pawn, but jumps.
Well, the second player wants to keep them, as long as he's the second player, he wants to keep them in this kind of
Position?
because
Okay,
he's
all
the
right,
one-
all right.
because in an all jumping game, he would be the one who would end up last. But
Uh-huh.
whoever makes the break like this loses.
Okay, so Aviv's theory is if the first player jumps, then
Second player jumps.
second player jumps. So if I continue on jumping, he will eventually win because of the number of cells, he says. But if at some point I decide to be stupid and move forward like that, I'm through again because of the previous game. Thank you. Well, what's the question I'm going to ask? Yeah?
Or maybe what would happen if the number of cells were different, or what is important to the strategy? I mean, is it the parity of the number of boxes in between the two, which is a fancy word for odd or even, and he always counted as even. So if you moved it forward, then there's always odd parity between the two. But if there's two spaces or zero spaces, then there's an even parity between the two, in which case you move.
Okay, so there is something going on, Victoria says, about what is the spacing between the pawns? Is it even or odd, and which spacing you would like to keep? Well, as we shall see from our discussion now, it is a little bit complicated to think of it this way. There is a lot of truth, a lot of bread in this, but there is a slight twitch there. Yes, Aviv?
If the number of cells change, basically it all depends on who wins the game if it's only jumps. Because
Very
whoever-
nice.
Because whoever makes that break loses.
I see.
So
Okay.
therefore nobody will make the breaks
All right, let's make a definite decision. There is one method that I believe all of you have seen if you came to my first lecture. How many people came to the game theory lecture in the beginning? 1, 2, 3, 4, 5. Okay. So, you guys know how to do these problems. This is a finite game, right? After several moves, there are no backtracks, so it will end. So, how do we encode such games? Do you remember? What was the way to solve these games? Suppose you want to be totally dumb and follow a way of doing all of those problems. Yes, Spencer? Yeah, the end, you are reasoning from the end game, right? Okay, but there was this problem, if you remember the monkeys and the bananas. Remember that problem? I'll just refresh your memory. Hold on. I'll tell everyone here so they know what I'm talking about. So there are 2 piles of bananas. Let's say 5 bananas and 7 bananas. Okay, and so 2 monkeys play the following game. At each turn, you can take, a monkey can eat either 1 banana from one pile, or eat 1 banana from the other pile, or eat the same number of bananas from the 2 piles. There was something along these lines, right? And so we're asking, does one of the monkey have a strategy to win? I don't care about the particular rules of the game. If you remember how we translated it, what did we use, Spencer?
You put it onto like a piece of graph paper.
A piece of graph paper, right. And we used eventually a rectangle with cells, right? So we made a table, right? And a table like that has 2 dimensions, right? A vertical one and a horizontal one. And each of these 2 dimensions meant something. What did they mean? Do you remember? Well, someone else. Yes, Victoria?
The number of bananas in each pile.
In each pile, how they diminish. So you start from the lower corner with 5 and 7. And then every time you take a banana from a particular pile, let's say from the first pile you'll move right, from the second pile you'll move up. Do we have the same problem here? We have how many pawns? Suspiciously 2, right? And each pawn eventually wants to get to the end somehow, right? So what is going to be my horizontal dimension? Yes, Aviv?
Pawn number 1.
Pawn number 1, more precisely? The leading pawn. Okay, well, that's the initial leading pawn, right? Because the pawns can switch their leading position. So we're going to mark one of the pawns, make it white, let's say. Okay, and every time it moves a square to the right, or 2 squares, we will move in that horizontal direction. And every time the black pawn, the second pawn, moves, we'll move in the vertical direction, right? So we need a table. Yes, I'm going to give you a table to all of you. So here is what the table will look like. Well, how many squares do I have? Yes?
400.
400. That's one of those nice square numbers that we saw in the previous circle. Why 400?
Because it's a 20 by 20 board.
20 by 20 board.
It's at 400 or 300 meters.
Okay, well, there is a little bit of discrepancy whether you need some of all of those cells. But just to make sure, we will have all of them. Now I have one of those. Let me check if I have any more. And if not, I have, yeah. I think I have better means for you. So, Aaron, give this to the girls. Okay, and they'll start. Now, there are 2 people here who have not been at the circle lecture, so you 2, right? Marina and Kenneth, right? You were not at the first circle lecture. No, okay. So I'm going to ask Marika to work with Victoria on the table, and you 2 are going to move here, and I'm going to talk with you separately, okay? So Marina and Marika, could you switch places? Right here, guys, make a table. you. Okay, so here is what we have done with the other kids. Can I have your pencil? One of them. Okay, so we need 20 by 20, right? Okay. So each of those has 4 squares, so we need how many of them? 5, perfect. Like this. So I'm going to draw it from your position. So in this direction will be the first pawn, okay? Let's say the white pawn, and in this direction, the black pawn, the second pawn, all right? So where are we initially? Let's see. Okay, so where is the first pawn? It's in position 2, right? Okay, and the other pawn is in position 1. So where on this table do I have this position depicted? So first pawn is in position 2. So it has moved right here, yeah? Second pawn is in position 1, it hasn't moved up. So the initial situation is right here, yeah? Do you guys see this? So this dot here means we are in position 2, 1. First pawn is in position 2, second pawn. This is like coordinates. Have you heard of coordinates? Okay, so let's play. Marina, make a move.
Could I use any pawns?
Yes. Okay.
Could I
So
move more than one?
no.
Okay.
According to the rule, just one. So where did you go from this point?
One space.
Where? Here or here? To the right. Yes. So you're now right here. Why? Because the first pawn moved 1 square. Okay, so make another move, more interesting. Well, if you can. Okay, what happened? It moved here, right? Okay, let's try to catch up. So I'll move this one once and then another, right? So what happened with this dot?
It moved up 2.
It went first here, right? No? Because the second pawn moved 1 square. Yes? So every time the second pawn moves, we're moving up. Okay, so this position here simply means first pawn is in position 4 and second pawn is in position 2. And then we move again. So second pawn is in position 2, but first pawn stays in position 4. Okay, now I want to make a jump. Okay, what happens with the jump?
Move diagonally.
The jump is a bit interesting here because the second pawn moves 2 squares, right? Am I moving diagonally?
No.
No, because this pawn stays, the first pawn stays, right? So you're moving 2 squares up, like that. Okay, let's make another jump. Remember, this is now first pawn and this is second pawn, right? Okay, so how would I depict this?
Moves right.
To the right, yes, because the first pawn. Make another jump. Okay, like this. Okay, so at any moment you can move either like this or like that, yes? Or if they are close to each other, like this, next to each other, you can make a 2 in one direction or 2 to the other. It's a bit complex to see where this is happening, but we'll talk about it. Now let's go to the end position. Okay. Okay, where would I depict this end position?
In this square?
Which one? This?
Yes.
Well, that square means that they're both in position 20, right? And that's not true.
And the square to the left or the bottom?
That's right, because we don't know which one is in front. It could be this or the other way. So these are, you want to land here, so these are winning positions, correct? Yes. So what we will do now on the board is we will reason backwards from these winning positions. We will figure out every place here, whether it's winning or losing, whether you want to land there or you don't want to land there. Okay? And depending on that, we'll decide what all of the strategies are in this game. Okay? So this is quite complex because we've worked with them for quite a while. So if you don't understand something, it's okay.
I don't really understand why the second pawn doesn't go this direction right from here. Why does it follow?
Because every point anywhere on this table actually does not does not mean the first or the second pawn. It means both pawns at the same time. Its position, let's say, what is this position here? Can you tell me? The coordinates of this point. If this is 0. So it is horizontally 5, right? And vertically 2. Yeah, so this point can be written as 5, 2. Okay, what that means is first pawn is in position 5, second pawn is in position 2. So using one point here, you can depict both of the pawns. That's why you have these two dimensions rather than just one. Okay, so again, if you don't understand everything, it's okay. You have not been, and this is the last problem we're doing of this type. I will show you right now. Okay, are we improving here? What's going on?
Trying to graph it.
Uh-huh.
You see, there are 2 dimensions here. 1 dimension for each pawn. Here, there's no pawn for each dimension.
By the way, while we're doing this, does anyone want graph paper? Okay, you want to see how the kids do it? Fine. So what we have talked about was reasoning from the end game. But before that, we need to figure out an encoding of this problem, just like the monkeys and bananas problem. There we go. Okay, there are some positions on this table that are off limits, that can never happen. Can you tell me where you can't be? Yes, Victoria?
Anywhere, I'm not sure, but
Along the diagonal.
you cannot be on the diagonal because then they'd be 2 places at once.
Okay.
And then
That is true. What I see on Victoria's picture is that she did the diagonal this way. Okay. I'm going to do it the other way because those people here are entrenched in their beliefs that 0, 0 is right here in this corner. So I'm going to do it so they understand what's happening. Okay. So if the 2 pawns are right in the beginning, where am I on this particular situation? In which place? Yes?
Either the square, that square or the square diagonal.
Well, I think it is exactly 1. Because from now on, one of our points is going to be white, and the other one is going to be black. So we will know which one is there. In the very beginning, let's say, we have black and white behind each other. Okay? That means that black pawn is in position, which one? 1, right? Is in the first square, and the white pawn is in position 2. Aviv, pay attention here. I know this is easy for you. Okay. So what Spencer was talking about is this point here with coordinates 2, 1. Okay? This is where you are initially. So every time I move to the right, it means that the white pawn is moving. Every time I move up, it means the black pawn is moving. Okay? So now Victoria said that part of this table is off limits, namely the diagonal. because the pawns cannot be in the same position. So we're going to cross this whole diagonal here. Okay. Now we want to encode all the moves. Now what are the moves in this game? Aaron?
You can either move up, down, or you can move along diagonally if you're next to the diagonal.
Okay, I like very much if you're next to the diagonal, but I don't like moving diagonally. Aviv?
You get to skip one of those crossed out squares.
Okay, we're getting ahead of ourselves. I don't understand anything what you're talking about. So, yes, Spencer.
We get to either skip or move forward.
Skip or move forward?
Wait, are you talking about the one dimension or the two-dimensional?
The two-dimensional.
When you're next
We
to
can
the
either
diagonal,
move
What?
right,
when you're
up,
Okay, hold on.
move right or up,
one.
and when you're next to the diagonal,
Uh-huh.
You can skip over.
you can
You
can't
move-
land over on the marked off square because it's off limits, so you just go over it.
So you're moving in which direction?
Well, what do you mean? Either
Kinda
right or
jumping
up.
over. Yeah, either right or up. Always.
Okay, so let's say I'm right here underneath this diagonal. What exactly does this mean in the original game? No. Let us everyone think. Okay, what is this position here? Let's count. I'm going to count. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So the initially first pawn, the white pawn, is in position 9. And in which position is the black pawn? Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8. What does it mean that the first pawn is in position 9 and the second pawn is in position 8? Where are we? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's first pawn, and that's second pawn, right? So now what the second pawn can do is jump over the first pawn. What exactly does this mean? We moved in which direction? Yes?
Up.
We moved up how many squares?
2.
Two squares.
Which is the same as skipping
Ah.
over that diagonal.
Okay, so now we understand. If we're underneath the diagonal, there is one very special move, and that move is, where were we? 9 and 8, let's say right here. The second pawn can jump over the first pawn, so it will go 2 squares up. Yes? Okay. Then what can happen? So now we have first pawn here, second pawn here. Yeah? What can happen now? Let's get this army here to work. What can we do in this stage here? Yes, Marina?
One could jump over the second one.
That's right. For example, one can jump over the second one. In which direction did they move on my table? Pawn 1 means the white is moving, right? And how many squares did the white move when it jumped? 2. So we are moving 2 squares to the right. So if for some reason I am above the diagonal, which means second pawn is ahead of first pawn, I will move 2 squares to the right, and I will be again underneath the diagonal. So the 2 pawns are squashed next to each other if you are either directly under the diagonal or directly above the diagonal. And these are the only special positions from which you can make these special moves of 2 squares left or up. Yeah? So we have several moves here to consider. More or less at any stage we can move 1 square to the right or 1 square up, as long as we don't land on the diagonal, right? If the pawns are next to each other, you cannot move the second one forward. Yeah? Or if we are directly underneath this diagonal, where can I go? I can go 2 up. If I'm over the diagonal, I can go 2 horizontally. Okay, well, that's it. So now we start thinking about the winning situation. Where is the winning situation? Yes, Victoria?
All the way down at 1920
Okay, or
2019.
2019. Okay, she said all the way down, but you remember she was working in a different direction. Actually, I would say all the way up, whoops, in either this position or this position, correct? Because this means the two pawns are squashed next to each other at the very end. We don't know which one is first, which one is second. Okay, so we call these positions winning. So let's mark them with plus. You guys know how to do this. Okay, yes, Victoria?
And you get into a plus, and if you move to a plus position, you win. And of course, if you move into a position where your opponent can get into a winning position from that move, you lose. So if you can move to one winning position from a position, that's a losing position. If you can move to only losing positions from a position, that's a winning position.
So what Victoria did is she gave a very good definition of what's a winning position and what's a losing position. Now, for some of the people in the audience who are seeing this for the first time, I have to say it depends. The position is labeled winning or losing depending on when you land on it. What does this do for you? So if you land in a position and you're going to be eventually the winner, that's a winning position. If you land in a position and you're going to lose, that's a losing position. Okay? So if I'm starting from a winning position, am I a loser or am I a winner? If I start from a winning position, am I a loser or am I a winner?
I think you're a loser.
That's right, I'm a loser. If I'm starting from a losing position, am I a winner or a loser? I'm a winner. That's right. So it works a little bit counterintuitive depending on how you perceive positions. So think about landing there. Do you want to land there? You don't want to land there. Okay. So we want definitely to land on one of these two pluses. Yes, Victoria?
Okay, so since on the very boundaries of the chart you can...
Come on, show us.
Oh, thank you. Anyway, on the very boundaries of the chart, you can only move to winning position, so you mark it losing.
Okay.
So losing, and because you can only move forward, and you move into a position where an opponent can move to winning position.
Mm-hmm.
So you move these two losing, and so you mark this plus because you can only, the only option available is the losing position. That may sound a little weird, but so it alternates because from here you can only, your opponent can only move to winning position. So, and so plus minus.
Okay.
Plus minus. That. Sorry if I sounded a little unfair, but it's kind of hard to explain. And so there's that.
So one needs to have a little bit of training with all of this. I'm talking to the two kids who have not seen it before. So we can talk about this later on, and I'm sure Vera can enlighten now that if she's interested in this. Okay, so we have taken care of the last row and column.
Also,
Okay. Now you have to be very, very careful.
Or jump, as we say, to
Winning position.
winning position. If your opponent moved you to here, then this is a losing position.
Mm-hmm.
So losing, and because here you can only move
Well,
to.
be careful.
Yeah, I'm thinking.
Okay, hold on. Let everyone think about this. What, this dot here?
Oh, sorry, I.
Hold on, they'll tell you and you'll write it. All right, that dot here, is it winning or losing?
Oh,
Shh.
if you move
Victoria.
to.
Let them think. You're ahead of the game. All right, the dot, is it winning or losing? In other words, do you want to land there? Yes, Aviv?
No, because if you land there, he can go to a winning position.
That's right. If you land here, your opponent can move to a winning position, and you are? Okay, so that is?
Losing.
Losing. Okay, good.
Sorry, it just
You have to have an image of a bad ending
after
there.
this point, it alternates, and I wrote it down on my paper just that I got a little confused.
No, it's
So-
fine.
From here you can your opponent can only move to losing position, so naturally you want to move to this position, and therefore it's winning. So losing, winning,
Okay,
losing,
you can
winning.
forget about that.
and it
So
all-
basically, we see a checker pattern of winning and losing positions after a while. Yes?
Yeah.
Okay.
And they're
Let's-
close to the diagonal
Okay.
percentages.
All right. So let me take on from here. Thank you.
Okay, thank you.
So Victoria not only is writing these winning and losing positions, but she also explains very well why she's doing each and every one of them. Victoria, can you tell us which school do you go to?
Vineyard High School, Livermore,
Okay, Vineyard. And which grade are you in?
11th.
Which one?
11th.
11th?
Yes,
But how old are you?
12.
She's 12. Okay. I'm going to speed up here a bit. Everyone tell me, what is this position? Everyone, come on. Losing. And then? Winning?
Losing.
Be very careful. Oh man, what are we gonna do now? So that's, which one was this one? That was losing. And then we have losing again, and then the checkerboard pattern. Okay. We're gonna move a little bit more, and then we'll see what's going on. Just a few more. What's this guy here? Okay, what is this? Do you want to land here?
Yeah.
Yes, because you can go from, you can force your opponent to go only to losing positions. So this has got to be a winner. Okay. And from there on, the checker pattern underneath. I'm not going to finish it. And we can think symmetrically on the other side of the diagonal, correct? This is going to be positive, negative, checker pattern. Okay. So really, the whole action here is taking place around this diagonal, right? Everything else is a checkerboard pattern. Yes, Victoria?
Processes along the diagonal, there is also a checkerboard pattern.
Okay. We can see we have plus, minus, plus. And right here I'll have a minus. Why is this a minus? Because you can move to this plus upstairs. This means, in this position, that the two pawns are next to each other. And one can jump. There it jumps, and it goes to a winning. So if you land here, you're in bad spot, because your opponent can go to a winning position. So let us do the checkerboard pattern quickly along the diagonal. Okay, is that right? Aha! Well, before I haven't done anything else and filled in the rest of the table, who will win? The first or the second player? Yeah? Why the second? Who starts on a winning position? The first player starts from a winning position and will be forced, therefore, to move to a losing position. Which means the first player will lose, which means second player will win. But how many strategies the second player has? Well, is it really one strategy? Yes,
Well,
Aviv?
Here's the thing. If you just keep it up along the diagonal, the second player,
You mean right underneath the diagonal?
no, you keep it next to the diagonal, so you only jump moves. It would be just
Okay, hold on. Let me feel what's happening above the diagonal so everyone can see them. Is that right? Yeah, okay. So let's do it. I don't really need to fill this last guy, right? But I can. Will never be here. Okay.
All right. So you see, if it keeps near the diagonal, then the second player
Well, that would be a first player's move, actually.
No, if it keeps along the diagonal, the second player will win.
Okay. So you'll go like this if you're just jumping,
The
yeah?
first player is going to have to make a breakaway from the diagonal.
Okay, so the first player will land on a negative, right? And they want to get away from this under, above the diagonal situation because they're going to lose here, right? So they're going to make a break for it. Where would they go from here?
Actually, they would make a break from a positive score because that's where the second player lands.
That's right, but they would make a break from a negative square.
They would make a break from a positive.
Oh, I'm sorry. There you go. I'm thinking the other way around. So a first player would have to start from a positive square. You're absolutely right, and would have to try to make a break from this. So where can you go from here? Well, to the right, yes. Or you can jump up, but then you will be back in that jumping position. So what is this one right here?
It's a negative.
It's a negative one because of our checkerboard pattern. You can check it.
And once you get in the checkerboard,
You mean here
yeah, the
or
checkerboard-
above?
The checkerboard pattern. The second player has the favorable position in a checkerboard pattern, so he wants to keep the piece in the checkerboard
Right,
because it's just losing money.
right. So,
So
yeah.
that's why he just wants to keep it away from the diagonal, which is why he moves the leading one forward.
Right. So one very powerful strategy of the second player is to do what? As long as the first player tries to break away from the diagonal, let's say the first player moves here, the second player does what? Yes, Victoria?
Moves back to just below the diagonal.
Oh, well, that's quite all right. Or, yes, Spencer?
The next square has to be a winning square.
If you are here, the second player has total control of the game. In what sense? Yes, Aaron?
You can never get back to the diagonal.
Yes.
You can always,
Move the leading pawn.
yeah.
This is what you guys were trying in the beginning. If the second player ensures that the pawns at any moment of time are 2 squares apart, so the second player can keep moving the first pawn, and the second pawn behind it will never catch up. So it will again ensure a win. So you're going to stay in the checkerboard pattern, either underneath or above it. If the first player is stupid enough to try to stay along the diagonal and keep jumping, he's still gonna lose, and very fast, because you'll be moving 2 squares at a time.
And one more thing.
Yeah?
I think that's the only strategy
It's the only strategy, but we just
from the for the only strategy to win.
Well, once you get off the diagonal, you can do it.
Because whoever makes the break from the diagonal will always lose.
But Aviv, I think Aaron has a point there. Once you're in the checkerboard pattern, you don't necessarily need to move every time to the right. You can try to catch up a bit with the second pawn. So there are lots of strategies here. You have to be very careful.
Keep it away from the diagonal. Just
Right.
get it in.
But again, if you happen to get on the diagonal, the only positions that you have to be aware of are those minuses. There is danger there because, for instance, let me show you. There is, let's say, this is a, no, that's a plus. That should be, yeah, that's a minus. Then this should be a minus, 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 right? Okay. So what would happen, for instance? Okay. So, for example, you have to be very aware of those minuses, yes? So if the second player is, let's say, on this, starting from this -1, right? Okay? He should never go back to the diagonal because he will land on a -1. This is the tricky point. Okay? So the 2 pawns can be 2 places apart from each other, but some 2 places apart from each other are better than others. This is a very bad place when they're 2 places apart from each other. Very bad position. From this position, the second player can lose if he moves them next to each other. So when you are trying to tell me some kind of parity argument about the positions between them, keeping them even, Victoria, you have to be very careful, because even some positions where they are even places away from each other are bad, like this one.
Sorry, just that I was saying this before I actually made the graph, so I thought.
But it is a very good point. In
It
fact,
seems like it's okay, so let's see.
right. It is a very good point, and actually I'm going to leave it for homework to figure out, is there some type of, and I'm going to use a word, invariant, some feature of this game that you would like to keep the same. Is it the distance between the 2 pawns? Is it this distance multiplied by I don't know what? You know, some kind of weird function. Is there such a function that you can concoct that would tell you whether you're in a good position or in a bad position? There are always such functions. Sometimes they're just simply very complicated. So you may not be able to find a nice formula for them. Okay? So think along Victoria lines at home. Figure out, is there something about the distance between the 2 pawns or something else that would tell you, are you in a good position or in a bad position? Without referring to this table. Let's move on, Victoria.
The checkerboard is separately L-shaped at each diagonal. There's one L showing losing positions, throwing it off.
Let's leave some bread for thought here. Because Victoria is going to solve it all for us now. While I'm setting up for the next problem, let's have a bit of introduction of some people here that participated very much. Spencer, where are you going to school? Crowden School of Music in Berkeley. So he apparently is very good in music. And what's your grade? 6. Are you the age that you're supposed to be? Yeah, what is it?
I'm 11, but I'm almost 12.
Okay, he's 11 but almost 12. Aviv,
I go to Prospect Share School.
where is that?
It's in El Cerrito.
In El
It's a
Cerrito.
private school.
Private school.
And I'm 13 and go to and in 8th grade.
8th grade. Okay.
I go to Maybeck High School.
Maybeck High School in
I'm in 11th grade and I'm 16.
11th grade and 16. Marika,
I'm in Canyon.
where is Canyon School?
Canyon Middle School is in Castro Valley.
In Castro Valley. So this is east of Berkeley.
I'm 13 and I go to 8th grade.
Okay. Kenneth,
Canyon Middle School, I'm 11, and I go to 6th grade.
6th grade. And Marina, she's going to 6th grade and she's 11. No. Huh? And you are. Okay. Some embarrassing moments to be put on the spotlight here, but they are over with and we can have now some more fun. I can turn this guy off for now. Can we have the lights back on? So let's try another problem. This time the guys who had advantage with game theory will have no advantage whatsoever. So I'm going to read it, and you can also turn to page 5 if you want to follow. Okay. So problem 1 says, a designer constructs a lampshade in the shape of a pyramid. The base of the pyramid is a hexagon with side 5 inches. The edges connecting the top of the pyramid with the base are 10 inches long. The designer wants to decorate all edges of the lampshade by gluing a narrow ribbon along them. He has a 90-inch long ribbon. Can we cover all edges without cutting the ribbon? I won't need this anymore, so we can take it down. So the first important part of every problem, of course, is to understand it. In order to understand it, what am I supposed to draw? That's right, a hexagonal pyramid. So I'm good at drawing hexagonal pyramids, and I'm not good at drawing some oval objects. So that should be good. Well, I'm going to make my life very easy. Whoops. That's not going to end up good. So how do I draw a hexagonal one? Something like this. So this is the bottom, yes? And where is the top? Top is somewhere here, yes? Can I project it to the board? Okay, so do we understand what this picture now means? We are looking at this lampshade from, let's say, above, right? Is everyone picturing this? I can draw the picture a little bit different, but I don't think it's going to make much of a difference. Yeah? So you're looking from top. Okay, let us see what we have in the problem. How long is this? Yes, Marina? 5 inches. Okay. And how long are the red guys?
10.
Okay, 10. So how long a ribbon do we need? 90. Everyone sees this? 6 times 10 plus 6 times 5, so we have 90. We need a 90 long ribbon. Do we have that much? Yes, we do. Okay, that's going to be a tight fit, right? So the ribbon has to go all around these edges. Yes. Well, somehow. And we don't want to cut it. Yes? Can we do it? Hold on. I want everyone to try it. So we want to cover, instead of looking at this pyramid, try to cover this one with your ribbon without cutting it. I want some interpretation of this. What really am I trying to do with this picture? Yes, Victoria?
You're trying to draw a vine around the 12 edges, and because it's only 90 inches long, you don't want to double back on yourself because then you'd run out of ribbon. So you have to cover all those edges without
Backtracking.
crossing over yourself. And so can you do that?
Okay. So the word that I like is taking a pencil and drawing this picture without doing what?
Crossing.
Well, crossing, I'm a little bit aware of
Tracing over yourself.
tracing over the same edge twice, okay. And without what else?
Lifting your pencil.
Lifting your
And
pencil.
also without doing any cheats, like folding over the corner of your paper.
Oh, okay. I don't have this luxury here on the board, so we're not gonna. But you guys be aware of that problem. So go for it. Try to draw this picture with your pencil without lifting the pen up and without traversing the same edge twice. Try it. No. Everyone honestly try it. No fancy techniques here, Viv. Go. Well, that's a nice picture, Aaron, you have there. How are we doing, guys? Do you have a pencil? Can I borrow 2 pens from the audience? Oh, okay. There we go. So I'll try to draw it here. And after you try very hard on this one, let me ask you exactly the same question if you had not a hexagonal pyramid, but a regular, what's that called, with a triangle at the bottom? A tetrahedron, yes? So let me draw for you a tetrahedron here. Okay. Try that one too. I'm going to squash this tetrahedron also on the board. So it's going to look like there is the base, and the top of the lampshade is in the middle. Okay, so try each of those. Did you manage?
I think that's impossible.
But you are backtracking here, right? It's impossible? Mm-hmm.
That's what I think.
Okay, so try now the other one. Do you know why it is impossible? Why?
Because, let's just count the number of vertices here with an odd number of lines coming out of that.
Oh, yeah. Try the other problem. I understand. I'm saying, yes, try the other problem. How are you doing?
Not much luck.
Not much luck. Well, that may mean something. So anyone successful? Anyone in the audience successful? You have an idea? Do you have an idea? Did you manage with this one?
No.
Okay, Kenneth says it's impossible. But how do you convince me? Because I'm really, really stubborn. I can't just take your word for it. Yes, Spencer?
I think I might have figured out the sixth. But
You may have figured out the sixth one? Okay, show us.
and like how prove not to do it.
Oh, okay. All right, how do you prove that you can't do it?
So you always end up, every time you do it, you always end up so that you have to split two ways, and one of the ways you can't ever reach again is like the only time you can reach it because you boxed it off from all the other ones.
You blocked it off. Right, so some places are bad. Okay, what are these places that are really bad?
Well, so if you take a right.
Show me a place on this picture there that it's bad.
So if you like make a triangle, for instance, the first
Yes?
and then if you go back down to the edge,
Uh-huh.
the next way,
Okay.
then you have to split two ways.
So he somehow wants to argue that this guy is bad. This is what Spencer is telling me.
If you already have made a triangle.
If you have already traversed one of its edges. Okay. Actually, I don't think I have another chalk, so I'm going to make this.
It would probably be easier if I drew it than if I just did.
Hold on, just hold on. I want everyone to see. You'll explain more than what I want. So what Spencer is saying is, if you have made, let's say, this triangle up here, okay, and then you try to come to this edge, like that, what would happen now? Yes, Spencer.
You have to go, if you go,
Okay, come here, come here.
so if you go this way, then you can keep going, but then this you can never reach this because everything that touches it the three lines that touch it are all taken.
Uh-huh.
And then, but if you go this way, then the three things that are touching this point are all taken, so you can't leave there, and then you're kind of stuck there.
Okay, so this guy is bad. Thank you. Now, in Spencer's statement here, go back. There were lots of ifs. If I have done this, and on top of that, if several things follow, then the situation is bad. But what if I haven't done those things? Maybe I can avoid doing them.
Actually, I guess I've just proven it for if you start from the middle.
If you start from the middle, he says he has proven it. I don't know, because I don't have to do this triangle first. I can, go. There is more. But I want a way to do all of these problems in one shot. For example, I want to do this one too, exactly the same way.
A couple of scenarios kind of.
Right, so one way of doing these problems is exhausting all scenarios.
Well, I didn't quite. I think I did something in the middle.
Okay, so you are between exhausting all scenarios and trying to apply some kind of reasoning.
Yeah,
We want to apply only reasoning. Okay, because I want to solve, when you go home and I give you a problem, I want you to solve all of them without sitting there for hours. Remember how they were calculating the sum of the numbers in the previous session? And they did it under 2 hours? Yeah. Okay. Yes, Victoria?
Well, isn't there a problem like this called the 7 bridges or whatever it was called, where you try to cross on to every island without stepping on the bridge, stepping on the same bridge twice and trying to get back to the same island that you started it, or was it using all the bridges?
Mm-hmm. Okay. Well, I guess she means the map of the city Königsberg? Königsberg. Okay, that problem? All right. So someone has been reading. Very nice. Okay, so I'm going to give finally the word to Aviv because he's going to be bursting here of displeasure. So what's wrong with this situation?
Well, you have to have a starting point and an ending point, right?
Okay, so starting and ending.
All right. And whenever you go to any other point, you go in and you go out.
Okay, so there is a middle point here. So I'm going to leave the starting point. At some point, I'm going to enter the middle point, and I have to leave it.
Right. Now, there are going to be at least like 4 middle points, which will have odd numbers of.
No. Keep telling me things about this middle point. What else can happen with it?
Well, you see.
Can I come back to it too?
All the points can be classified as starting, ending, or middle.
Oh, very good. So there is the starting point of our path, the ending point of our path, and all the rest are called middle points. So let's talk about the middle points.
All right. So since the starting and the ending can't cover all of the points that have 3 lines coming out of them.
Uh-huh. By the way, what are these points called?
Vertices.
They're called vertices. And what are these segments called? Edges. Well, that's if you want to put fancy math terminology on it. And what's this picture called? A map. A lampshade. Okay, that's getting there. A diagram. A graph. Okay, well, that's the fancy math word. A graph. So we have vertices. These are the points. And the edges, a special sort of guys, they connect some of the vertices. They don't connect all, for example. These two are not connected, right? So a graph is a picture like this with vertices and edges. Okay, Aviv says one of these vertices will be the starting, the other vertex will be the ending point. And how many vertices do we have? 7? We have 7 indeed, 6 on the base and 1 on the top. Does everyone see this, Marina? Okay, so we have 7 vertices. So one of those is the starting, the other one is the ending, and?
At least one of those on the side is going to. you know, actually at least four of them on the side are going to have to be a middle point. But let's just look at one. A
Like
middle
this
point
one.
on the side. Okay.
This one? Okay.
Doesn't matter which one.
Okay.
So then, when you enter it
I'm entering it.
from any of the, then you exit it by another one.
Okay, I'm exiting
That-
it.
But then you still haven't covered it all yet, so you have to enter it again.
Okay,
So
you
when
have to enter again.
There's no exit.
There is no exit. Okay, so can this be a middle point in your path? So middle points are described by saying you must enter and exit. You can't stay there, right? So right now here I have two segments, or two edges coming out of this middle point, middle vertex, right? Let's say after a while I come back to it and then I have to exit, yes? Then after a while I come back to it and I exit. And let's say that's the last time I'm visiting this point. How many edges did I draw? How many?
An even number.
An even number, that's right. You enter and you exit, that means two more, and two more, and two more. Every time you enter and exit, two more. So you need an even number. So a vertex that has even number of edges is going to be called an even vertex. Okay, so let us identify the even vertices here. Can someone point to me the even vertices? Yes, can you circle it for us? That's right. That's the only even vertex. Its so-called degree, the number of edges is 6, right? So I can draw the number 6 right here, right? Okay. So all of the other guys are called odd vertices because they have how many number of edges? 3. So everywhere else I can draw the number 3. Okay. So if I'm going to draw this path that I want, right, I've got to have a bunch of middle vertices. In fact, at least how many? 5? There are 7 points. Okay, so I have to have 5 even vertices. But how many do I have? I have 1. In fact, which are the bad vertices in this graph? The even or the odd ones? The odd ones are the ones causing abstraction. If I pick an odd vertex, can it be a middle point? Marika, what do you think? No. So odd vertices can only be what? What? Which one? Starting or ending points. The even vertices can play the role of what? Yeah? Only the middle? Okay, well, let's talk about the starting point. What happens with the starting point? How many edges can start from it? So you leave it, okay? That's 1. Then you want to come back to it, that's 2, but then you want to exit, 3. Okay, I want to come back again, 4, but I want to exit 5. I want to come back to it, 6, I want to exit 7. Okay? What? It's an odd one unless something else happens with that vertex. Can the starting vertex actually have even number of edges? Let's say 4. Can't it? Okay, I leave, I come back. I leave, I come back. And I never leave. There is one situation where this can happen. Aaron is shaking his head. When can this happen? I want my starting vertex to have 4 edges. When can this happen? When you end there too. That's right. So there's this special situation when your path is actually closed. You start and end at the same vertex. It can be even. It has to be even. So even vertices can be anything. You just have to be careful. If they are starting and ending, they have to be the same thing. Okay. So let us draw to a conclusion here. Middle guys can be even or odd. I want everyone's attention here so we can finish quickly. So if I'm looking at the middle vertex, is it an odd or an even vertex? Yeah? That's right, it's an even because it can't be odd. Okay, so all of the middle vertices are even. Okay. The starting and the ending guys could be both even or odd. So what's the restriction here? There is one restriction that is very powerful that says you can't have this.
You can't have more than all but, and you can't have less than all but two even vertices.
Okay, well, say it now positive. Quite correct. Use the word odd vertices. You can't have.
That's the only way I can think of it.
Okay, Aviv, help.
You can't have more than 2 odd vertices.
That's right.
Yeah, that's right.
Okay, well, let's write it down, and that's called a theorem. So let's say that theorem is actually called, I'm going to call it Eulerian graph theorem. Okay, I'm invoking the name of a mathematician, Euler, right? Okay, so what's an Eulerian graph? Well, what do you think?
What you drew? Like the little the little pyramid things that you did?
No, I don't think anything on the board I've drawn is Eulerian. They're all bad. This guy is not Eulerian.
Is it a representation of an Eulerian?
Nope. No matter how I draw this graph, it's not going to be Eulerian. Yes?
It's one where you can do the thing.
You can do the which thing?
The ribbon thing. Where you
The
draw
ribbon
Where
thing.
you draw it without lifting
Nice.
the going over a line.
All right, so we need a definition here. So the nice thing is called an Eulerian path, right? But that's kind of defining things with the same term. So definition, an Eulerian graph is a graph where? What can we do? We can travel along all of the edges without doing what? Without going on the same edge twice. And we're not jumping, we're not doing anything fancy. We're just walking along the edges. That's right, so I'm not jumping. I'm continuing to walk. Okay, where we can traverse or traverse all edges one after the other without backtracking on any edge. On any edge. So in other words, we can do the ribbon thing. Every time you think about an Eulerian graph, you're thinking about that ribbon that you don't want to cut and you want to cover all of the edges, right? So let's go back to the theorem. If you have a good graph, that is a graph that has this ribbon thing, right? So if a graph is, we decided to call it Eulerian, but we really think of the ribbon property one. Okay. If a graph has the ribbon property, then, Spencer?
Then it can't have more than 2 vertices with an odd number of edges.
That's right. So let's compile this as in. It cannot have more than 2 more words.
Odd vertices?
Good. Okay. Then it cannot have more than 2 odd vertices. I'm almost done here. Okay. So, does this lampshade qualify as having the ribbon property, being Eulerian? Yes?
Well, it has 6 odd edges and
Odd
odd
vertices.
Sorry.
Okay.
And so
6 happens to
the
be.
theorem says by the ribbon property it cannot have more than 2 odd vertices. Now, is 6 greater than 2? Yes. So, done.
You can't do it. Perfect. Well, let me push a little bit further for homework. Okay, we failed to do the ribbon thing. That is no cutting, can't do it. What's the question? What is the, yes?
How many times do you have to cut it?
Well, I can cut it a lot of times and cover the whole
Wait,
thing.
what's the minimum amount?
Minimum number of cuttings that you have to cut this ribbon and still cover it. Okay, so you have to take care of those nasty odd vertices. And that's going to tell you how many. I'm going to leave this for homework. And last remark, very, very advanced. Now, this theorem goes only one direction. If you already know what's happening, that is, if the graph has this Eulerian property, then it can't have more than 2 odd vertices. Well, you know, big deal. This is if you already have that stuff. If you already know if the graph is good, right? But suppose I throw at you a graph with exactly 2 odd vertices. Okay? So let's think of such a graph. There is such a graph, right? I have 3, 3. These are the odd vertices. Is this graph Eulerian? Just trace it in your mind. Looks like it is. Right? So the big question is, if a graph is with this property, in other words, if a graph has 2 odd vertices, is it Eulerian? So that's a much bigger theorem to prove. And there is one extra thing that you have to say here, connect it, and then it becomes a big theorem. And the answer is yes. So you can read about this in the book, and maybe we'll talk about it later. So thank you for your participation here.